setjmp.h is a header defined in the C standard library to provide non-local jumps, control flow that deviates from the usual subroutine call and return sequence. The complementary functions setAim and LongJMP provide this functionality. A typical use of setAim, LongJMP is implementation of an exception mechanism that exploits the ability of LongJMP to re-establish program a thread state, even across multiple levels of function calls. A less common use of setAim is to create syntax similar to coroutines. Member functions. setAim saves the current environment at some point of program execution into a platform-specific data structure that can be used at some later point of program execution by LongJMP to restore the program state to that saved by setAim into jmp_buff. This process can be imagined to be a jump back to the point of program execution where setAim saved the environment. The return value from setAim indicates whether control reached that point, normally from a call to LongJMP. This leads to a common idiom: if handle LongJMP *POSIX. 1 does not specify whether setAim and LongJMP save and restore the current set of blocked signals. If a program employs signal handling, it should use POSIX sig setAim sig LongJMP. Member types. The C99 rationale describes jmp_buff as being an array type for backwards compatibility. Existing code refers to jmp_buff storage locations by name, which is only possible for array types. Caveats and limitations. When a non-local GOTA is executed via setAim, LongJMP, normal stack unwinding does not occur. Therefore, any required cleanup actions will not occur either. This could include closing file descriptors, flushing buffers, or freeing heap allocated memory. If the function in which setAim was called returns, it is no longer possible to safely use LongJMP with the corresponding jmp_buff object. This is because the stack frame is invalidated when the function returns. Calling LongJMP restores the stack pointer, which, because the function returned, would point to a non-existent and potentially overwritten corrupted stack frame. Similarly, C99 does not require that LongJMP preserve the current stack frame. This means that jumping into a function which was exited via a call to LongJMP is undefined. However, most implementations of LongJMP leave the stack frame intact, allowing setAim and LongJMP to be used to jump back and forth between two or more functions, a feature exploited for multitasking, compared to mechanisms in higher-level programming languages such as Python, Java, C++, C#, and even pre-C languages such as ALGOL60. The technique of using setAim, LongJMP to implement an exception mechanism is cumbersome. These languages provide more powerful exception handling techniques, while languages such as Scheme, Smalltalk, and Haskell provide even more general continuation handling constructs. Example usage. Simple example. The example below shows the basic idea of setAim. There are main, which in turn calls second jumps back into main's call of print. Subroutine gets called first is never printed. Main gets printed as the conditional statement if is executed a second time. Exception handling. In this example, setAim is used to bracket exception handling, like try in some other languages. The call to LongJMP is analogous to a throw statement, allowing an exception to return an error status directly to the setAim. The following code adheres to the 1999 ISO C standard and single Unix specification by invoking setAim in a limited range of contexts, as the condition to an if, switch or iteration statement. as above, in conjunction with a single, or comparison with an integer constant, as a statement. Following these rules can make it easier for the implementation to create the environment buffer, which can be a sensitive operation. More general use of SetAim can cause undefined behavior, such as corruption of local variables. Conforming compilers and environments are not required to protect or even warn against such usage. However, slightly more sophisticated idioms such as switch are common in literature and practice, and remain relatively portable. A simple conforming methodology is presented below, where an additional variable is maintained along with the state buffer. This variable could be elaborated into a structure incorporating the buffer itself. This program's output is calling first, entering first, calling second, entering second, second failed, exception type, first failed, exception type. 1. Cooperative multitasking. C99 provides that LongJMP is guaranteed to work only when the destination is a calling function, i.e., that the destination scope is guaranteed to be intact. Jumping to a function that has already terminated by return a LongJMP is undefined. However, most implementations of LongJMP do not specifically destroy local variables when performing the jump. Since the context survives until its local variables are erased, it could actually be restored by SetAim. In many environments, idioms such as if LongJMP can allow a called function to effectively pause and resume at a SetAim. This is exploited by thread libraries to provide cooperative multitasking facilities without using setContext or other fiber facilities, whereas setContext is a library service which can create an execution context in heap allocated memory and can support other services such as buffer overflow protection. Abuse of SetAim is implemented by the programmer, who may reserve memory on the stack and fail to notify the library or operating system of the new operating context. On the other hand, a library's implementation of setContext may internally use SetAim in a fashion similar to this example to save and restore a context after it has been initialized somehow, considering that SetAim to a child function will generally work unless sabotaged, and setContext, as part of POSIX, is not required to be provided by C implementations. This mechanism may be portable where the setContext alternative fails, since no exception will be generated upon overflow of one of the multiple stacks in such a mechanism. It is essential to overestimate the space required for each context, including the one containing main, and including space for any signal handlers that might interrupt regular execution. Exceeding the allocated space will corrupt the other contexts, usually with the outermost functions first. Unfortunately, systems requiring this kind of programming strategy are often also small ones with limited resources.